everyone. Welcome to your homework for tonight. Tonight we're looking at rational and irrational numbers and looking at a couple of released CAPE items that'll help you on the test. So, a rational number, as we went over last week, is the ratio of two integers. And a ratio, remember, looks very much like a fraction. It's a comparison of one number to another, where those two integers are a and b, and they are integers and they do not equal 0, or b does not equal 0, rather. Right? The word rational comes from the word ratio, so that's why we say it's a rational number. Um, it has a ratio, produces a ratio. And a ratio of integers produces either other integers, terminating decimals, so decimals that end, like 1.25, or repeating decimals, like 0.33333, which we know means 1/3. There are a couple of common repeating decimals that are helpful to know, like 0.66666 is 2/3. But those are still rational numbers because we can represent them as a fraction with a rational number in the numerator and the denominator, an integer in the numerator and the denominator. An irrational number then is not a rational number, but it's a number that cannot be written as a fraction/ratio. These have decimals that go on and on without a repeating pattern. So pi is a perfect example of an irrational number. Pi is 3.14159265359, so on and so forth. Square root of 2, square root of 3, lots of our square roots are going to be irrational numbers. If you try putting them in your calculator, let's see what we get. In your TI-84, your square root is on the square button. So second square makes it nice and easy to find. Let's try 2. So that's, notice, 1.4142135. It doesn't appear that there's any pattern here. And so we could estimate that to be 1.41, I believe is what it was, to the nearest hundredth. But it would keep going on and on and on, right? If we do the square root of 3, we get 1.7320, right? Again, you don't see like an obvious pattern there. And, oh, that was not correct, 7.3. And so those numbers are going to continue on and on without any repeating pattern, and we can't represent the square root of 2 as a fraction. So there are some special rules. These are the laws of the rational and irrational numbers. The first one is that if you add a rational number with a rational number, you get a rational number always. So if I add 5 plus 1/3, I get 5 and 1/3, right? If I add 2 plus 4, I get 6. I get another rational number. If you add a rational number with an irrational number, you will get an irrational number, okay? You'll get an irrational number because if we add, for example, 5 plus the square root of 2, you're going to get, looking back up at what that was, is 1.41. You'll get 7.41 and so on and so forth, right? So you're going to create another irrational number. If you add an irrational number with an irrational number, you will almost always get an irrational number. So the only time that that would not be true is if, for example, you were to create a number that would equal 0. So if you were to say, for example, pi plus negative pi, right, we would get 0. If you multiply a rational number with, oh, sorry, so this is actually a counterexample. An example would be if I were to add pi plus the square root of 2, right? You're going to get an irrational number from that, right? Let's take a look at this example. So second pi plus the square root of 2 gives us an irrational number, right? So if we multiply a rational number with a rational number, you get a rational number, right? So if I multiply 2 times 1/5, I get 2/5. It's a ratio of two integers. If you multiply a rational number with an irrational number, you will get an irrational number, right? If I multiply 2 times pi, I get 2 pi, or I get 2 times 3.14, blah, 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 blah. And so I'm just multiplying all of those decimals by 2 then, and so that's going to be an irrational number. Or if I were to multiply 3 times the square root of 2, right? You're just multiplying all those decimals we get from 2 by 3, and so you're just extending that number on and on and on. It'll still be irrational. If you multiply an irrational number by an irrational number, you might get a rational number. So here's an example. If I multiply the square root of 2 times the square root of 2, I'm going to get 2, because this would be the square root of 4, which is plus or minus 2. Then I get a rational number. So if I'm multiplying an irrational number that's a square root times itself, then I will get a rational number. And so in some cases, such as this example, an irrational number times an irrational number gives me a rational number. But if I were to multiply, for example, pi times the square root of 2, or the square root of 2 times the square root of 3, I'm still going to get an irrational number. So the only time really that when we multiply an irrational number by an irrational number and get a rational number is if we're multiplying that number by itself and it's a square root. All right, so a couple reminders and review about square roots. Square roots are the inverse operation to squaring, right? So when I take a number 2 squared, I'm multiplying 2 times itself, right? When I take the square root of 4, I'm taking the square root of 2 times 2, and so I'm undoing that square and I get 2, or plus or minus 2. When with a perfect square, we get a rational number, right? So if I take the square root of 4, like I just did, we get 2. That's a rational number. If we are doing a non-perfect square, we get an irrational number. And when we get an irrational number, we have to estimate to the nearest hundredth or thousandths. So if you use a calculator, determine the square roots of the following numbers. So let's look first at the square root of 11. So second square root of 11, 3.31662479. So I'm going to round to 3.32. And then let's try the square root of 13. Second square root 13. 3.605555. All right, so we'll say 3.61. Okay. And I'm going to change these to like curvy equal signs because it's about, right? Those are not the exact number because the exact number goes on and on and on. It's very rational. Sometimes a number has a factor that is a square root, and this can help us to simplify. So the example is 12. The square root of 12 can be broken up into the square root of 4 times the square root of 3. And then the square root of 4 can be positive or negative 2. So that's positive or negative 2 times the square root of 3. So let's look at 27. 27 can be broken up into 9 times 3. And so we can also rewrite this as 9 square root of 9 times square root of 3, which means this can be plus or minus 3 times the square root of 3. And so this just helps you to simplify this, particularly if that were a fraction, then you could use that to make your calculation a little bit simpler. So a lot of times we try to do this. It's a way of just the way that we would simplify, for example, 6 over 10 to 3/5, right? This is a way that we simplify our square roots. Without a calculator, we can also estimate a square root based on the perfect squares around it. So as an example, the square root of 11 would be between the square root of 9, which is the perfect square of 3, and the perfect square of 4. So the answer would be between 3 and 4. Since 11 is a little bit closer to 9, right, it's only 2 units away from 9, and it's 5 units away from 16, I'm going to say it's less than 3.5. When we compare that with what we got above, we got 3.32, so that's pretty close, right? So you can use your other square, your perfect squares, to kind of estimate. So without a calculator, if we estimate the square root of 17, well, the square root of 17 is between the square root of 16 and the square root of 25. Those are our perfect squares, 4 and 5, which means it's between 4 and 5. Now 17 is way closer to 16 than it is to 25, so I might estimate this is 4 point like 0 something or 4.1-ish, right? So let's go ahead and do it. So the square root of 17 gives us 4.123. That's lovely, 4.123. Um, and so again, you can use your perfect squares, the ones that you know, to estimate ones that are not perfect squares. It's not going to give you the exact number, but again, it's a pretty good estimate. All right, so then, oh, sorry, this is where we write this. I made this. That's where it goes. All right. So now we have some CAPE practice questions. There is always a question on the CAPE about rational and irrational numbers, and really this is just one of those things that you need to memorize the definition and know what they are. If you remember that an irrational number is an example is the square root of 2 or pi, then that's super helpful for you to remember the rules, right? Because you can always reason through it. So it says, which of the statements are true? A, the sum of two irrational numbers is always irrational. B, the sum of two irrational numbers is sometimes rational, or sorry, the product of two irrational numbers is sometimes rational. C, the product of a rational number and an irrational number is sometimes rational. D, the sum of two rational numbers is sometimes irrational. So what's really important with this is that you read carefully because all of these say some kind of qualifier. So always, sometimes, 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 right? Be careful with that. So let's look at which ones we know are not true. The sum of two irrational numbers is always irrational. Well, we looked at the example of 2 plus, then a square root of 2 times plus a negative square root of 2, which gives us 0. So there are cases sometimes in which irrational numbers added together do not make irrational numbers. We have a couple of counterexamples for that. B, the product of two irrational numbers is sometimes rational. Well, we didn't know above that if I did the square root of 2 times the square root of 2, I would get 2. And that's a rational number. So sometimes it is. And so that one seems like our best one. But again, don't just pick the first one. Let's keep reading. The product of a rational number and an irrational number is sometimes rational. That is never true. Because if we were to multiply 2 times the square root of 2, for example, again, all we're doing is multiplying all those decimals by 2, right? So all of those decimals will still continue on with no pattern, but they'll be multiplied by 2. So this is not true. The sum of two rational numbers is sometimes irrational. No, the sum of two rational numbers are always rational, right? 2 plus 3 is 5. That's a rational number. So the sum of rational numbers is always. That's where this is wrong, okay? So be careful with these sometimes always ones, right? Because you need to really read carefully. If you can think of a counter example, right, then you need to right, like in this case, it's not that it's sometimes irrational, right? It's never irrational. That's how we would make that correct. So B is our best answer. For part B, it says which of the statements using operations on rational and irrational numbers always results in a rational number. So 100% of the time, which of these produce a rational number? So irrational plus irrational, no. We know irrational plus irrational is almost always going to give us an irrational. Irrational divided by irrational. That will sometimes give us a rational number, right? So for example, if I did the square root of 2 divided by the square root of 2, that's going to give me 1, right? But not always. Not always. All right, irrational plus irrational. So up above we said irrational plus a rational number, right? Our rule here will always get us a rational number. All right, and so that is true. It will always result in a rational number. And then also it says rational divided by rational. So that's if we were to like do 2 divided by 3, right? Or even 2/3 divided by 1/3. This is also going to always give us a rational number. So for this one, which of the statements, there's two possible answers here. These will both always result in a rational number. All right. Question 2, select the drop-down menu. So in these would be like little click things. You click on and then you click in the different boxes, right? The sum of 1/3 plus the square root of 5 over 3 is rational or irrational. So this is a rational number plus an irrational number, which means that this is going to be irrational, and that's because the sum cannot be expressed as a single fraction, right? So I cannot make a fraction with a rational numerator and a rational denominator because this would be 1 plus the square root of 5 over 3, right? This is still irrational. And so that is still going to be an irrational number because I can't represent this as a fraction with integers in the numerator and denominator. The quotient, 20 divided by the square root of 16, is, so 20 divided by the square root of 16 is plus or minus 4. For the purposes of this, let's say it's 4, which is 5. 5 is a rational number, right? That's a regular old number. We can represent it as 5 over 1 or 20 over 4. Because the quotient, so is it because it has the square root in its denominator, or is it equal to an integer? It is equal to an integer. So yes, it has that square root in its denominator, which we can then take. But if it was the square root of 3, then it wouldn't be rational, right? But because it's the square root of 16, which we can make 4 or negative 4, it makes it equal to an integer. Question 3. And this one is really important. I said make sure to clearly explain your thinking. For the purposes of this video, I'm going to kind of give you some notes and ideas here, but I want you to really write this out and practice writing answers to these types of questions. So it says two real numbers are defined as a equals 0.444444, b equals 0.35435555435554. It says determine whether each number is rational or irrational. Is the product of A and B rational or irrational? Justify your answers. I'm going to type for this one just for the ease. So A is rational because it is a repeating decimal. And then remember, we need to prove that it can be represented as a fraction. So 0.44444 is very close to 4/10. So let's see if we can figure out what that fraction is. Like I said, 0.44 is close to 4/10. So what if we did 4 divided by 9? Because we know 4 divided by 8, we know what that is. So 4 divided by 9 gives us 0.4444. So that is it, right? And when you're looking at trying to decide what those repeating decimals are, it can be helpful to kind of think about what it would be close to and then adjust up or down from there, okay? So let's take a look. Oop, that's the wrong one. All right, so A is rational because it is a repeating decimal. It can be represented as 4 out of 9. B is irrational because it is a decimal that does not have repeating values and cannot be represented as a ratio or fraction. Now notice that both of these have these dot, dot, dot after it. That ellipsis means that it goes on and on and on, right? So our assumption is that this is going on and on and on. Now, one thing that would make A a little bit clearer that it is a rational number if there was a line over that 4, because the line over the number means that it is repeated. It goes on and on and on. But at any rate, B is irrational because it has a decimal that doesn't have repeating values. We can't find a fraction or a ratio that would represent it. And then it says, is the product of A and B rational or irrational? So the product, which means multiplication, of A and B is irrational because we can cite the rule. So because a rational number times an irrational number gives us an irrational number. And you can also further elaborate by giving an example of what that would look like. So if we multiply 4/9 times B, we would be multiplying all of those non-terminating, non-repeating decimals by 4/9, but those decimals would continue on and on without a pattern and could not be represented by a ratio or fraction. Actually, we can just say by a ratio. Okay? This is an example, right, of my thinking. You can also give examples, right? So like I gave you examples above. If there's one that's like, could it sometimes? Yeah, it could sometimes be something because, right? And explain, giving an example. Um, an irrational number times an irrational number can sometimes give us a rational number because the square root of 2 times the square root of 2 gives us 2. So in this case, it does not, though. Last but not least, your code word for today is reason, because the word ratio very largely connects often with reasoning, right? So when we say rational or irrational, it's someone who has reasoning or doesn't have reasoning. So if that helps you to remember the word, and irrational numbers don't have reason, right? They just go on and on and on. All right, happy homeworking, and I will see you Monday.